I kind of I got landed with this because originally the discussion was that we were going to give a little talk on chemistry for maybe about 12 people, of the subset of the V4VAR group, and now it's escalated into something. So I have absolutely zero training in chemistry since I was about 15. So the only thing I know is just because I had a somewhat sticky brain and I can't remember things. Well, I used to. I don't remember so much now. So Jim can help me if I get into trouble. So the story of chemistry starts with alchemy. So can I get rid of these people because I can't see my own captions. So it's about knowing how to prepare things, but not really knowing what you're doing. So here we have what looks like a couple of monks. I think they might be making brandy, because they're definitely distilling, and distilling is one of the big things in alchemy. But if we just move on from that, but they had, at least in Western alchemy, they had these beliefs that the basic elements were earth, water, air, and fire. And in this process of making this philosopher's stone that was going to let you turn lead into gold, they had a series of processes to do. Now, some of them make sense. They're the kind of things that people still do in laboratories, and some things less. However, they were people with missing very basic understanding of how chemistry works. They were still extremely skilled in processing things on an industrial scale. And one of the things was glass. Glass allows you, of course, apart from making windows and things to drink your wine out of, it makes all your laboratory equipment. And right there in Murano, I went there when I was about 7 years old, and they let me try and blow a bottle. I can imagine that now. So some aspects of glass making haven't changed. I mean, without really understanding anything about the atoms and the processes, they knew how to do it just by trial and error. And chemists, people who might, people like Glover, who's had a salt named after him, he didn't have a laboratory. He was just a traveller. He'd walk around making notes about glass makers and dyers and so on. And he was basically a recorder of what artisans did. Obviously, another type of thing that was done on a large scale was dyeing. So people would become very skilled at the using of natural materials for dyeing. This one is this is actually in Fez in Morocco, and when it's they go home, they say, "Where's Ahmed?" So you have to have a look around and make sure it's not in one of the tubs. Leather dyeing. I imagine that, in somewhere like, Viking, around York, probably they dyed leather in a very similar way. So some things don't change much. Now I've condensed the entire history of chemistry into a single page here. Alchemy came in different flavors. So in sort of China and India, the basic beliefs were somewhat different. So they can't all have been right. But if one condenses the progress from basically not really knowing why certain reactions happened, or basing it on completely false assumptions, what was actually needed was a proper definition of what is an element. So as Boyle said, those primitive and simple bodies of which the mixed ones are said to be composed, and to which they are ultimately resolved. So these are not the elements of alchemy. You don't need to remember all this, but it moves on through until we get to Mendeleev with his periodic table, which is really the basis of modern chemistry. And once that was in place, people were enabled to do all kinds of things that were not previously possible. And here is the modern version of the periodic table. It runs going from horizontally, we get from the lightest, lowest atomic weight elements to the heaviest. And if we run down the columns, they are all elements that have similar properties. Along the bottom here, we have lots of dangerous things that are radioactive. And interestingly, here, these some of these gases, the so-called noble gases, are very heavy, but they're still gases. We might come back to this. That's what I wanted. So here is the kind of view of the atom that I was taught at school. So in the middle we have the nucleus, which is a collection of pool balls stuck together, which we can't divide that up, but it has various electrons in orbit. It's tempting to think of it rather like planets going around a sun, but it isn't really quite like that. So we think of the simplest possible atom you can get is hydrogen. It has a single protein with a positive charge in the middle and a single electron with a negative charge. Helium, you double up on the nucleus, but you gain 2 neutrons as well, which have the same weight as a proton, but they don't have an electrical charge in 2 atoms in its orbit. But the basis of the periodic table is that these each nucleus has, according to how many protons and things it has in it, has a different number of electrons. And the first so-called shell or orbit has 2, the second one 8, and the next one 18. I can't explain to you why it is those numbers. That's how it is. So they are not really in a simple orbit like a planet. They may be moving around. I think that's why they say a shell, because it's moving around in a 3-dimensional sort of shape. And the hotter it is, the faster they move. And as the temperature goes up, the electrons jump from one orbit to another one. So a very hot atom, the first shell may be empty, and the other ones, they're pushed out to the other orbits. So we're committing an anthropomorphism here. We're saying the atoms are happier with full shells. So if we go back to those noble gases, the outer shell is always full, and it makes them very, very non-reactive. They don't want to interact with other atoms. But in the case of oxygen, it only has 6 atoms in its outer orbit, which makes it hungry to get a couple more to satisfy that requirement. So one of the ways is that oxygen atoms don't exist as a single atom. They join up with another one, and they share a couple of atoms in their outer orbit. Lots of gases do that. And in the case of water, so each hydrogen atom has only 1 electron, but it can satisfy the requirement for them to have two atoms in their orbit, and for the oxygen to have 8, which forms, as we know, a pretty stable substance. It's not easy to smash it up. So Lego isn't really quite right, but it's this concept of having valency bonds, say different number of sockets or places where they can join together, is kind of useful, because you can plug atoms together in various ways, and given a particular set of atoms and number of electrons in their outer orbit, some things are possible and some things are not. So you can't actually well, you can, under extreme circumstances, change atoms, like in the center of a star, atoms can be changed from one substance to another. But in normal circumstances on our planet, you can't destroy an atom. But you can rearrange them. So if you want to know about smashing up the nucleus, Colin will be able to tell you about that. So atoms are rearranged by naturally occurring events, biological events, and by human manipulation. But the number of atoms always remains the same, but it might involve a change of state, like they might get very hot or they might drop in temperature. So generally when things crystallize, they move into a lower state of energy and the temperature goes down. And very important thing, particularly in organic chemistry, is polymerisation. That's where things join up. So a so-called monomer molecule, that is one that doesn't repeat itself within the same molecule. They join together to form chains or three-dimensional networks. So in my little drawing here, my single molecule is a cube, but it can join up into a long chain. And then there's another extremely important type of polymerization, which is in the benzene ring, which is something that puzzled scientists for a very, very long time. Just did not make sense. This guy, August Kekula, how do you say it, had this dream about the serpent devouring itself, i.e. that the carbon atoms were arranged in a hexagon. And that has been a transformative development for organic chemistry. And these substances became known as aromatic compounds because some of them smell nice, you know, but they don't. I mean, it's not a defining feature of aromatic compounds. And this one, you can buy one of these if your friend's just had a baby. This one squeaks when you squeeze it. I don't know if they're helpful visualizations. So these carbon atoms arranged into rings can form all kinds of important substances. This material is just coincidentally I stumbled across it. It's actually dimethyl sulfoxide, which is an interesting solvent because it can dissolve gelatine without swelling it, which I think it might have applications in restoration. But the problem is it's a very powerful solvent and strips varnish, and it's used in paint strippers. Also, nice happy coincidence, I found a picture of a lignin molecule. No way am I going to try and explain what all of these reactions are, but it's rather to say that point out that you can, you know, there are many possible different arrangements of these hexagons. And on the right here, there's a very uniform arrangement of them into a sheet of graphite. So every single ring is identical, and they kind of plug together to make a very strong material. So I feel very alone here. I've got no sense of whether anybody's even hearing what I'm saying.
We're with you.
Oh, good. So here's a very simple idea is that
Georgia,
yes,
if you put it not full screen, then you can have a banner with different people with a video.
Okay. No, it's all right. Just so long as I know that that it's not that I'm not just kind of talking and nobody's hearing anything.
No, we are.
Okay. Good. So here's a very simple idea that actually the properties of substances are actually strongly related to their molecular size and structure. So gases and liquid or solid, you know, they're different sizes of molecule. What the point they melt at, their boiling point, the hardness and color, these are all related to their structure. There we go. So here's a very easy diagram. So the size of the rectangle is an indication of the size of the molecule. So if they are otherwise similar atoms or molecules, so I mean molecules, not atoms, they will start out as a gas, but as you increase the size, it will start to be a liquid and a more viscous liquid, wax-like, low melting point solid, harder, and you can move on to things like diamonds that you don't really melt, and they're very hard. So in organic chemistry, the most basic one is the alkane series that it comes from oil, from crude oil. And the smallest one of the series is methane, which is one carbon with 4 hydrogens attached to it. Like in, of course, it doesn't really look like this picture, but that does give you the idea that the bonds are arranged at 120-degree angles, so they're sort of tetrahedrons rather than a kind of the flat look that this diagram would imply. So make up long chains. So these ones are all gases, but when you get to 8, they're a liquid. So that's octane is the thing that we're going to stop running our cars on very soon. And when you get to over 22 in length carbons in the chain, then they become solids. I don't really know what you do with those solids. But that's it makes the point that the different size of molecule changes its very basic properties. But you can also smash up polymers. So one of the most obvious ones is, as in this picture here, in an oil refinery, you're taking the crude oil up to a very high temperature and you're making it actually break up into constituent parts, which you then separate out by fractional distillation. That is saying you select different, according to your height up the tower, you select a different point for which you're going to collect the condensate and separate it out into products of different molecular size. Down here we have a woodworm dining, maybe it's a Stradivari it's dining on. So animals can digest all kinds of polymers. Bacterial action and hydrolyzation, that's I mean, an example of that is when collagen, which is this stuff that our skin and tendons and things is made out of, can be broken down into gelatin, which is water soluble. So it wouldn't be good for our skin to be water soluble, obviously. Another thing is to look at, start to look at what are things generally made of, and a good start is to look at the Earth's crust. So if you just step outside your door and pick up the first stone that you see on the ground, you'll find it's principally aluminosilicates. That's a mixture of silicon dioxide and an aluminium oxide. And if it isn't, it's something a little bit special. So each one of these items can be found more or less in isolation in natural, occurring naturally in mountains and volcanoes and places. So that this area will be inorganic chemistry. These are things that are not in any way connected with the life cycle. Whereas organic chemistry is mostly to do with the life cycle. It involves chemistry of carbon, oxygen, and hydrogen, and other things. So most of the chemistry, basic chemistry we've been taught in schools will be about inorganic chemistry. What is sodium chloride, that kind of thing. if you want to know what things are, particularly things like minerals, you can use this technique called EDAX. So sometime around the late 80s, I had a client who worked for Gado Chloride in Warrington, and he had access to some of this analysis equipment. I gave him some samples of wood ash to look at. So we see, interestingly, one of the previous uses of wood ash was for making potassium carbonate. So you burn the tree, collect the ash, put it in water, and then you drain the water off and crystallize it until you have a high purity potassium carbonate. But interesting to see, there's nearly as much calcium there as there is potassium. And there's a whole array of other kind of interesting things, including sort of phosphorus and sulfur. So these are things that the tree has picked up while it's growing. But in another sample of wood ash, I think this one was a washed one. Here's our old friends, aluminium and silicon again. So, you know, an ash residue actually is already a source of aluminosilicates, along with some of these other things in a small quantity. So it's partly a problem with the technique, but if you take these sorts of samples, you find they're actually very variable. You know, even if you took from the same bucket of ash you collected from a fire, you take out different bits, you'd find that you got a different result for a different sample. But we can cope with that sort of thing, can't we? Then you get a bit of a plant, and you find it's you're almost certain to have got something with polysaccharides in. So polysaccharides are polymers made up of glucose molecules, which I have to believe it look like this picture, or then they join together, as in down here, I hope you're seeing my mouse, and then into other kind of longer chains. So in trees, like hemicellulose has molecules ranging from 50 to 3,000 glucose molecules, and cellulose is 7,000 to 15,000. So that's a very big molecule. And I don't know, it didn't say where I got this information, but molecules between 3,000 and 7,000 are probably called quasi-cellulose. So the tree grows, it forms glucose. The glucose joins up into ever longer and longer chains of molecular size, and it forms part of the binding, particularly the higher molecular weight hemicellulose is a significant part of the binding material, equivalent to Tim's epoxy resin. And cellulose is pretty damn stable. I mean, you can burn it, and you can break it up with very strong chemicals or animals with a specialized digestive system and destroy it. But hemicellulose, particularly the lower molecular weights, can be more easily broken down. In fact, over time, about maybe 1% per century, hemicellulose just spontaneously decomposes into water and carbon dioxide, so it can leave the wood as a gas. But if you say put it in hot water, it will turn to glucose, and then you have to wash that away. But other enzymes and things, particularly for fungi and things, can also break it down. So this is an area that is of interest to us, like wood treatments. But it isn't a magic bullet, really. So you should always start with good wood anyway. But it seems likely that removing some of the lower molecular weight hemicellulose is helpful, because it's hygroscopic, so the wood will take up less moisture. But whatever you do, you have to be very careful not to damage the lignin. So in theory, lignin can be made stronger. I mean, in the Yamaha patent for their high pressure steam treatments, they claim that the availability of OH ions in the steam actually strengthen the lignin. But I don't know, this is somewhat lacking in proof or a really detailed knowledge of what the reactions are. But another useful part of wood treatments is reducing internal stresses. So wood always has internal stresses, and you don't know they're there until you cut some of it away. So both heat, steam, and humidity cycling are advantageous for that. And then you find an animal, well, almost certainly you're going to come up with a bit of protein of some kind. So analogous to polysaccharides being polymers of glucose, proteins are a range of different types of amino acid and different size polymers of those. But they differ from carbohydrates in that they contain nitrogen. So the collagen is a source of gelatin, and that's one obviously that is of interest in violin making. And drying is not a chemical reaction. So,
sorry, George, I don't hear anything anymore. I'm afraid then. Can you hear me?
I can hear you. Should I just stop the sharing for a minute? Do you hear me? No.
Okay, I don't hear anything, and I'm worried that the recording is broken. So because. Okay, I'm sorry.
What should I do?
I don't hear anything. So then it stopped.
I've had the shared screen, George.
So I don't know if the recording will work, and I may have to restart Zoom.
I don't know what to do. I mean, I could shut it down and.
George, do you mind to stop? I have to restart Zoom, and so I don't want to lose the recording. So I will stop everything, and I will join you in 10 seconds. What's going on? Is in the body talking?
Wir hörten einen Podcast von SWR 2. Mehr Beiträge auf swr2.de oder in der SWR 2 App.
Okay, sorry for this. Don't know, there was some. I start again. Actually, it's still recording. Perfect.
Okay. Shall I carry on?
Yes, sorry for this. I don't know what happened.
Okay. that didn't work. Slideshow. Oh, damn, it's not starting. There we go. So is there somebody who wishes to speak?
No, it's only me, George. I'd lost my picture and it's now come back again. So there's something very odd happening.
Oh.
I'm turning my mute off again. Turning my mute off.
Yeah, mute yourself. Yeah, so we were talking about glue drying, and that is not actually a chemical reaction, because the gelatine has this property of being able to swell and absorb an enormous amount of water and then become mobile when it's warmed. But being a long chain type protein, what happens is when it dries, the chains are entangled together and they no longer slip about and they're no longer fluid. So it reverts to a jelly-like stage, and the more the water departs, the more solid it gets. So there's an example of a very, very direct connection between the behavior of the material and its molecular structure. But other proteins we use, like for example, egg albumin and casein, are globular type proteins. They're sort of all jumbled up into a ball and not in these long chains, which makes them not as strong as an adhesive, but it makes them good for sealing and binding purposes. So don't really need to know this, but as you know, I mean, casein occurs as a calcium salt in milk. Then it can be detached from the calcium by chemical intervention or enzymes, but then can be made soluble again by the addition of calcium hydroxide, and then the calcium hydroxide absorbs carbon dioxide and becomes insoluble again. So this makes it a very useful material in some ways to make an insoluble protein layer, and it's used in certain types of fresco painting. It is really quite a durable material. But it's quite different from gelatine in many ways. But the other important plant materials are resins. And our favorite one is pine resin, which can be collected in various ways. It either is exuded from the tree as a gum. You make a cut into the bark of the tree and the stuff just comes out. And it's a mixture of things, of small molecules of a type known as terpenes, and resin acids, and you get your dead ants, tree bark, water, and whatever else. So that needs some processing to become useful. But in other times, it was processed by extracted in other ways, and another way was to build a clay base somewhere in your forest or just outside your forest, probably a better place. And you stack the billets up in a heap, cover them in soil and turf, and then burn it like burning charcoal. So with a shortage of oxygen, enough heat is generated to drive the resin out of the billets and let it flow to the bottom of the clay base along a channel into a pit. Some people just boiled bits of wood in water, but it's a pretty inefficient method. But by far the most common method is through chemical methods, particularly with caustic soda. That's sodium hydroxide. So it will dissolve in that, and then it's re-acidified to precipitate it out. It's known as tall oil, and this is the lowest quality of rosin, at least from our point of view. But if you're a big chemical company, this is the source of rosin for the various materials that you process from it. So we really want the first one. However, everything is more complicated. So the two main things that you get from that exuded gum, or known as gum rosin, is the spirit of turpentine, which we use as a solvent, and the rosin, which we use to make varnish and put on our bows. But the way we distill it now simply did not exist before somewhere around the middle of the 19th century. I don't have an exact date for that. But the way it's done is that you choose your fraction that you're taking off by the temperature of a stream of superheated steam, and that will carry it over into the condenser. And the current is very useful because there's no, when you heat these materials, there's no significant vapor pressure. So if you boil water or alcohol, the gaseous phase of it occupies a very large volume. So there's a flow leaving the still. But with the turpentine and rosin, this is not so. So that's why the steam distillation makes a very big difference. But before that time, all the decompositions were a result of direct heat, in which case you get a different set of products, which include water, acetic acid, the turpentine spirit, rosin oil, and maybe a host of slightly different combinations. So they can, to some extent, be separated by fractional distillation, but in general, it's the lighter ones come across first. So you'd start with a lower heat and then gradually increase it. So one of the important points to note about this is the kind of spirit of turpentine that we can buy so easily now did not exist before the 19th century. So this is some of these diagrams come from a catalogue from the Arizona company. I just forget its name. Yes, they're called the Arizona Chemical Company. And I don't know if they still exist, but they most of what they did was involved in processing tall oil rosin. But usefully, they list some of the better known reactions. One of these is called decarboxylation, which is where this COOH group, which is an acetic acid radical, is removed by heat. So maybe the products are different if you use the palladium catalyst, which is what that means. But actually the product is rosin oil and other slightly modified versions of the resin acids. So this is another such reaction known as disproportionation, which means that some of the hydrogen gets removed and you replace. Actually trying to see what has happened. I think in the last one you can see that all the double bonds have moved to that that hexagon ring. Hydrogenation is the opposite of what we normally do, but it is a process that can make the resin more stable. So if you want a resin that's not colored from the heat treatment, but you want it to have a higher melting point and be a bit harder, hydrogenation is one of the ways to go. So I've given a whole page to rosin oil because it's rather, I find it very interesting. I got interested in it from reading the Louis Condac's final summary report. And of course, I couldn't buy any rosin oil, so I started distilling it. And I built a still from an old lawnmower roller and various other bits and pieces. And I started distilling it. So there are people who sell it, but I've not seen anything since NRI stopped producing it. I've not seen anything that I really believe is actually rosin oil. They seem to me to be just other balsam type materials. So it has a very distinctive smell, and you smell it when you do soldering with solder that has a flux in the core. So that smell is of the very heated rosin, and it's useful as a flux because when it's formed, it's an exceptional wetting agent, and it'll spread out, cover the surface, and protect it from oxidation. And then that allows the solder to flow into those places. So at one time, it was produced in very large quantities, was recognized as a contaminant of linseed oil. So people would bulk it out with rosin oil and sell it, make more money. But it was used in impregnation of various things like electrical cables and seals around windows. Excuse me. So that's when used in wood finishing, this is a very interesting property, because with the low molecular weight stuff, you cannot build up a layer. It simply spreads itself out one molecule thick as far as it can go. And it has, when you put it in a container, it has the meniscus is the other way up from water. Like water tends to reject the container it's in and hump up, pulling itself together. Rosin oil goes the other way. It tends to cling to other things. So it has this peculiar blue-green fluorescence, yet it transmits yellow-orange, and that goes away as it becomes oxidized. And then it won't dissolve in alcohol or mix with it, but it is a strong solvent. So when we cook rosin, I think a lot of people are not really aware of the of rosin oil and what it's doing. So as we cook it, this disproportionation and dehydration, it makes it more stable, higher softening point, more color. Yet while you're doing this, you're forming rosin oil. So in my mind, the business of cooking rosin is about the management of that rosin oil, exactly what you're going to do with it. Because you don't want it just left in there, otherwise it'll cause the varnish to crackle in a more extreme way than you would actually want. On the other hand, if you deliberately want to have a crackler, then make sure there's some rosin oil in your varnish. But it takes time, it can't sort of set or change in a few days. It's a long process. So when I first started cooking varnish, a lot of people did what we call the frying pan method. That is a container with low walls, so that pretty much you just kind of boil off the low molecular material, and then you get left with something that's pretty stable. But it's very wasteful. Oops, didn't mean to do that. But we quite a few people now use something. This isn't actually mine. This is Roberto's system. For some reason, I simply cannot find a photograph of my own. But I cook mine in a little stainless steel container, and there's a half a meter long borosilicate glass tube. So the rosin the rosin oil vapor will rise up around here, and you can see it as a sort of slightly milky looking cloud, and the little drops condensing on the wall of the tube and dropping back in. So over quite a long period of time, that rosin oil mixes with atmospheric oxygen, and it returns back into the mix to form a rather different resin material. You're probably all familiar with the Bill Fulton method of starting with oil of turpentine, putting a fish tank bubbler through it to oxidize it, and then you put it through a dangerous decomposition process. So it's a kind of terpene polymer resin, which is quite good, but probably no historical basis to it. It's also very dangerous to make, like you can easily get an explosion or an uncontrollable fire with that. So I rather favor this sort of refluxing method, because there's very little wastage. You get a very nice clear resin with a good color, and it's strong. You can also use it with a very, very small amount of oil. So this is my little book on linseed oil. So what all vegetable oils and animal fats have in common is they have 3 fatty acid chains stuck to a glycerol molecule. They differ in the number of double bonds in the chains and the length of the chain. So all chains end up in a carboxyl group. But the principal component of linseed oil is linolenic acid. That has 18 length fatty acid chains, and the double bonds at positions 9, 12, and 15. Now, other oils are similar, like they have different numbers of double bonds, but you know, linseed oil is very much favored for use in varnish. So obviously, as we know, they start out as liquids, but in the process of drying, what happens is that they form links across from one chain to the other. So rather than the chains joining up into one very long chain, they link across to each other. So a way to visualize the process is to, oops, go back one, is to cook a pot of spaghetti, leave a little bit of water in it and so on. And then at that point, you can pour it from one container to another. But if you leave it to set, it sticks together in a big lump. And so it's becomes like an elastomer. And that is very much what happens to linseed oil when it dries. And how am I doing for time? Oh, running out. Just to talk a bit about managing reactions. So let's say, for example, we're going to make a madder lake, and we're going to start with aluminium sulfate. That's the single salt, not the potash alum. So the basis of the reaction is that if you add a certain amount of potassium hydroxide to it, the aluminium hydroxide will precipitate out because it's not soluble, and then you'll be left with a solution of potassium sulfate, which is soluble and can be washed away. But of course, in real life, it's more complicated. The aluminium sulfate has water of hydration, 16 and sometimes 18 waters of hydration. And potassium hydroxide, well, it isn't that, and except when you open the container. So if you happen to have a proper chemical laboratory with fresh stocks of these materials, you'll find that your potassium hydroxide is at least in part potassium carbonate with some added water. So it makes this process of trying to guess exactly how much of one we need, it makes it very difficult. However, we can make estimates. So if I know the composition of these materials, and I can look up their atomic weights from the periodic table or somewhere else, very easily done, that I can get my spreadsheet, and I can work out the molecular weight for each of these substances. In fact, even in the case of potassium carbonate, I can make an estimate for the amount of water of hydration it may have. However, it's still an estimate. So the way forward is you can do this calculation as though your potassium hydroxide was pure. You could say, well, I'm going to use potassium carbonate instead. You make these assumptions, or you can find a way where it's ultimately not critical to weigh out the exact quantities. And that is possible because of the precipitation reaction. So we look at our molecular weights, calculate how much we want. So my sums come up with saying if I start with 100 grams of aluminium sulfate, I'm going to need 53.3 grams of potassium hydroxide, or maybe a bit more if it's potassium carbonate. It's going to be, I'm assuming, 3 waters of hydration, so again 165.7 grams. However, the method is if you take your potassium hydroxide, dissolve it in water, and then into that you dissolve as much alizarin as you can. And there could be many other different dyes. You can even use dragon's blood, things like that. And then you make up a solution with an excess of aluminium sulfate, and you pour the aluminium sulfate solution into the alkaline solution until it starts to precipitate. And then you go very gently and you try to go just sort of to that point or a tiny bit beyond. Then after that, the job is to wash it to get rid of the unwanted material like potassium sulfate, which we don't want in our end product. And this, you can do that to oil as well. But of course, adding the metal to the oil makes it is a very strong sedative, and it may make it no longer liquid. The difference is, instead of knocking off the carboxyl group from the resin acid, you knock it off the end of the fatty acid chain. So if you dissolve your resin will need roughly 18 to 19% by weight of potassium hydroxide, which makes a water-soluble soap. Or if it's oil, the glycerol is removed. Then you co-precipitate it out and wash it. It's a messy business. It sticks to everything, and it's quite difficult getting it dry. But they make very, particularly the resin ones, makes a very useful product. But in fact, it's often made an assumption that you must go for 100% saponification, like stick as much aluminium to it as you can. But I don't agree with that. I think it's actually 10 or 20% is better, because you've got a much more manageable material. So all you have to do is put in, you know, if 100% saponification requires the 18 or 19% of potassium hydroxide, put in 1/10 of that, or 20% of it, and that will define the degree of saponification. So it means you can get away with a combination of heat treatments, refluxing, and metallization. And you don't need that much aluminium to have a strong color. In fact, with the resin, you don't even have to add the alizarin in the alkali solution. You can simply add it in alcohol solution after you've dehydrated the resin. So I've given you an sample of quantities down there. I'm getting very near the end. This is quite good timing, isn't it? And wood staining, yeah, well, I mean, one of our favorites is potassium nitrite. But it has a problem, like things with nitrogen and oxygen tend to want to become nitrates. So your potassium nitrite is all the time is fighting to get another oxygen out of the air and become the nitrate. And it's things like heat, enough heat to break it down, makes it revert to nitrite, or UV light. So one of the tricks seems to be mixing it or having a separate wash of potassium carbonate. And we can, from the molecular weights, we can make a little bit of a guess as to how much we might need to balance out the acid radical. And another one we use a lot is potassium, well, not so much now, potassium dichromate, which is a very powerful oxidizing agent, but is an extreme health hazard. So we're getting pretty much to the end now. So just like to remind you about safety working with chemicals, because you know, some of these things really are quite dangerous. They can cause, you know, like if you get potassium hydroxide on your skin, you get a nice nasty burn. some of the acids will rip a hole in your clothing. So pretty much with everything, you don't want it on your skin, certainly not in your eyes. And inhaling dust. So if for example, you used potassium dichromate in a stain, if you then go to scrape or sand the wood after that, then you're getting this stuff airborne and you're likely to inhale it. So obviously masks and cleaning the whole area up after you work with it are important. So I would say, you know, anything you're thinking of working with, any chemical process you're thinking of doing, do your research first and make sure that you're not going to set your workshop on fire, or you're not going to give yourself cancer or some other problem. And that's it. So can I exit screen sharing?
Thank you, George.
Stop the share. I didn't think I'd get through it all.
You
I really
want
didn't
to
think
say
I'd
more?
get through it. No. Oh, I think that's quite enough. Well, I think it'd be good if we have a little bit of time to talk about some of these things and anything that's arisen from it. I mean, I kind of selected some things that interest me, and I tried to give a little bit of a sense of what different chemicals are like, where they come from. So it's completely experimental. So anyway, we can talk about it now, and other people can answer the questions. Yes, anything?
Okay, there were
Colin
quite
looks
a
like he
few.
wants to say something.
There were quite a few things in the chat, but maybe some people would like to ask the question directly or react directly. Anybody raising hand? No.
George, it's
Oh, yes, Philip has something to say. Unmute yourself, Philip. If you want
Okay,
to speak.
George, thank you. George.
You're welcome. Oh, what a beautiful workshop.
Oh, thank you. You should come. Hey, do you, can you say anything about the boiling point of the rosin oil?
About 280 Celsius.
Thank you.
But it comes in slightly different molecular weight. So a higher molecular weight would have a higher boiling point.
Okay. Andreas has a question.
Encyclopedia.
Sorry. No, it's just like there is a delay. So I started when you started. Is that finished? Because Andreas has a question.
Okay, George. I didn't get the main issue of your table with the rosin oil. You want to have the rosin oil in, or you want to have it out?
If I'm going to keep it, if I'm keeping it, I want it oxidized and converted into a colored resin.
Okay.
I don't want it left as a rosin oil, because it can cause the funny things to happen to the varnish. Because it takes a long time to absorb oxygen from the air naturally.
So that's the reason why you're cooking it with a 500 millimeters glass tube to have it oxidized and then fall down again.
Yes, exactly.
Okay, now I got it.
It's called refluxing.
Mm-hmm. Okay. Mm-hmm.
So many people are simply not aware of it. But if you cook, even if you put some rosin in a jar and put it on an electric ring at 120 C, you'll find rosin oil collects on the lid of the jar. It's impossible to heat it without it forming. So, but I think most of these varnish making operations are performed with zero awareness of this happening. Okay. So it's very, very important to manage what happens to the rosin oil in the reaction.
So that, yeah, you're totally right. If we just cook the rosin at 120, 140, there's always this smeary thing on the aluminum foil lid, which resembles on at the stuff formerly being sold by NRI. The second question. The second question.
The way they made theirs was they passed the guy Reg Lawrence who made it.
Yeah.
He put it in an ordinary sort of still with a small kind of neck, but he passed a current of nitrogen through it. So he ended up with these a very fractionated version of it. So the first one, the very thin type, was like the stuff I made with in an iron still. So the iron is acting as a catalyst with the production. So there's another thing, like say, you know, if you cook your rosin in a cast iron pot, that will tend to accelerate the production of rosin oil.
That would be that stuff of dry cooking, which makes rosin oil, or you just try to cook it at 280 degrees to get rosin oil?
No, it forms at lower temperature than that. You don't have to heat it that hot.
Okay.
But it's difficult to distill because it has no vapor pressure. It just sort of hovers above the surface, and it doesn't have any sort of pressure to push its way out of the still. So if you distill it, you need a still that moves into a very big sort of condensation area. More like the kind of like the alchemists at Alembic. So they knew what they were doing. They had good practical chemists, but they didn't know how it worked.
Okay, thank you.
Harris?
Sorry, I didn't listen to you. I wanted to ask something about. I wanted to ask something about something I read in the book Stradivari Varnish. In there is a varnish study for the Messiah violin, Stradivarius Messiah violin. And on the lower part of the F holes, the wings of the F holes of the lower part, there is a lot of cracking, a lot of cracks of the varnish. And in the book, the author suggests that this may be caused because the bottom layer of the varnish wasn't dried completely before the upper layer was applied. Can you comment on the chemistry of such phenomenon?
Those kind of white sort of crystalline stuff that we were shown around the inside of the F holes, it looks like some type of efflorescence. So that can occur when something is sort of soluble enough to move around a structure, and then when it comes to an open space, you know, everything sort of gravitates to that point. So you see the efflorescence of little crystals growing on masonry and so on. But I don't know. Without analysing it, I really don't know. It doesn't look like anything to do with calcium, because that doesn't typically behave like that.
Okay, could there be an indication of this rosin oil you mentioned?
No, I think that's very unlikely.
Okay.
That's I mean, other things that look a bit like that is the acidic acid that is formed from amber, but I don't know. It's kind of odd that it's only there. I mean, that takes a bit of explaining, like why hasn't it emerged somewhere else where the varnish surface has been broken?
I see. So the only way to know what is going on is by examining the varnish itself, chemically, right?
Let's scrape off a few cubic millimeters of it, give it to a good chemist, and they'll tell you exactly what it is.
Yeah, I think it's highly
That would be
unlikely we will be able to do that, especially for a violin.
Ask Greg.
Well, perhaps there's a non-destructive way of analyzing it.
George,
You want to comment on it?
I have a sense that maybe you two are talking about different things. George is talking about, if I got it right, the white powder inside the edges of the F-hole.
Yes,
And
that's what I thought you meant.
Maybe asking a question about varnish on the outside.
Those cracks I'm mentioning are on the upper side, but I think that they also appear somewhere in between those areas. Maybe they because in the book there is no photograph of the inside of the F-hole. But I don't know, maybe Craig would like to comment exactly what is happening there.
Well, I would say that the white residue on the inside of the F-hole certainly is not original product from Stoppani. We'd see that on other instruments, and that's just my thought. Someone said heel polish, but I'm not sure about that either. The thing to do is to actually get a bit off and to study it, and I believe that actually that could be possible. We didn't do it in Cremona when we had the instrument because we didn't have permission or time to do it, but so you know, that's another step, another research to be done.
Okay.
If I may, Jean-Philippe is telling me privately that some of what you're discussing will be in what he's going to present. So maybe we could pursue the discussion after Jean-Philippe's talk.
I think that would be a good idea, because then there'll be a whole collection of questions that come up.
Yeah.
George,
so I'd like, so sorry, Jason, can we move on?
I can't ask a question.
Make it quick.
What is happening when you're putting lime into the rosin pot while you're cooking it?
Yeah, well, what's happening is it's replacing the carboxyl group, and it makes the resin, it increases its melting point, makes it more stable. So limed rosins are quite stable for use in varnishes and paints, used in car paint for a long time.
And does that have anything to do with the rosin oil? Does it change the rosin oil?
It inhibits the formation of rosin oil. So if you saponify the rosin, it won't form rosin oil.
Okay. So just before we move on, I wanted to show you, I need to move a bit. This picture, I took it last year in Ville-Favard. Lovely flowers. So please join in next year.